Hello everyone, and welcome to the video on section 16.2. Section 16.2 covers three different methods of counting. The first method is called the multiplication rule, the second method is called permutations, and the third method is called combinations. So even though this section is in the probability chapter, this section doesn't deal with probability directly. It deals with counting. So your first question is probably, what do we care about counting things? Why do we need methods of counting? Here is the answer. If E is an event in a sample space S, the probability of E is defined to be the size of E divided by the size of S. What does that mean? That means that if you want to compute the probability of something happening, and in this case that something is the event E, you need to be able to count how big E is. You need to know the size of E. And you also need to know the size of S, the universe in which E lives. So calculating a probability, which you will start doing in the next section, boils down to being able to count. If you can't count, you cannot calculate probabilities. So that's why this section is dedicated to three different ways of counting things. It's necessary to be able to calculate probabilities. Here is an example of tossing more coins. This is an example we've seen before. If we toss a coin 3 times and separately record the outcome of each toss, the sample space is given by these 8 outcomes. You can flip 3 heads, you can flip 2 heads followed by a tail, a heads followed by a tail followed by a heads, etc., all the way up to 3 tails. So in this case, with this sample space, we can just list it and we get a capital N equals 8. We can literally just say there are 8 things here. So counting this sample space is not hard because it's literal counting like you normally do, right? 1, 2, 3, 4, 5. Okay, so now let's look at an expanded version of the same idea, but we're going to toss a coin 10 times and record the outcome of each toss. In such an example, the sample space S is really big. So if I were you, I would imagine writing out the sample space for this example, flipping a coin 10 times, and compare and contrast it to this example. If you toss a coin 10 times, then you're going to have one outcome that looks like H, 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 H. Okay, so 10 heads. But you can also have an outcome like HT, HHT, TT, HTT, or something. You know, there are just many, many ways of writing down a sequence of H and T's of length 10. Okay? In this example here, writing down sequences of H's and T's of length 3 doesn't take very long. But as soon as you start flipping the coin 5 times, 6 times, 10 times, it becomes exhausting to write all of those things down. So just imagine in your mind, right? You should be picturing the sample space here, tossing a coin 10 times, listing it out like this. Okay, it's very long. You have 10 H's here, you'll have 10 tails here, and in between you'll have a bunch of other stuff. Again, something like TTT, HH, TTT, HT. You know, a bunch of stuff like that. So in this case, the sample space is too big to write down. So if you can't just write it down and count what's there, how do you figure out how many things are in there? How do you count the size of S without actually counting it one by one? Here is what you do. Each outcome in S can be described by a string of 10 consecutive letters where each letter represents either a heads or a tails being tossed. So here's an example, right? T, H, H, T, H, T, H, H, T, T. That means I flipped the tails, then I flipped the heads, then I flipped another heads, etc. So this is a sequence of length 10 here, right? There are 10 symbols, one symbol per time you flip the coin. This is a single outcome in the sample space. Here is one way you could flip a coin 10 times. But of course there are many more ways, aren't there? To count all of the outcomes, we will argue as follows. There are 2 choices for the first letter, either a heads or a tails. 2 choices for the second letter, again, either heads or tails. 2 choices for the third letter, and so on, all the way to the 10th letter. The total number of possible strings is therefore found by multiplying the number of choices for each letter. And you'll notice this says 2 to the 10th. 2 to the 10th is 2 times 2 times 2 times 2 times 2, etc., 10 times. So if you actually wrote this 2 to the 10th out, you would have 10 2's staring at you. 1 2 per choice. Right? So you had 10 separate choices, right? Heads, tails, choice 1, heads, tails, choice 2, heads, tails, choice 3, etc. All the way up until the 10th letter. You just literally multiply the number of options per choice together. And so in this case, you have 2 times itself 10 times. And the size of the sample space is more than 1,000. Okay, so again, when you're doing 3 flips, the size of your sample space was 8. That is manageable. You can write it down and count it. If you wanted to write down the sample space for flipping a coin 10 times, you would have to write down more than 1,000 strings of H's and T's, all of length 10. Okay, that is not practical. You don't want to sit there and write those down and then count them. What we just did, that previous example, is an application of what is called the multiplication rules. The multiplication rule. And this is what that rule says. If there are m different ways to do x and n different ways to do y, then x and y together in that order can be done in n times n different ways. So let's come back to this previous example. Suppose I said flip a coin twice and keep track of the order in which things happen. So HT is different from TH. Okay? How many ways are there to do that? Well, there are 2 ways to do the first stage, right, your first flip, and 2 ways to do your next stage. So there are 4 ways total to combine the 2 stages. So here, what you should think of is that X is like stage 1 of something and Y is stage 2. But then the number of ways you can do stage 1 followed by stage 2 is simply take the number of ways you can do stage 1 and multiply it by the number of ways you can do stage 2. Okay? In other words, when something is done in stages, the number of ways it can be done is found by multiplying the number of ways each of the stages can be done. So notice here now, if you add on a stage 3, so let's call that capital Z or something. Let's say you can do stage Z R different ways. Then doing X followed by Y followed by Z, to count the number of ways you can do that, you would just add on a times R right here. Number of ways of first stage is M, number of ways of second stage is N, number of ways of third stage is R, so M times N times R would count the number of ways you can do stage 1, followed by stage 2, followed by stage 3. So here's sort of a toy example. Dolores is a young saleswoman planning her next business trip. She is thinking about packing 3 different pairs of shoes, 4 skirts, 6 blouses, and 2 jackets. If all of the items are color coordinated, how many different outfits will she be able to create by combining these items? Well, to answer this question, we must first define what we mean by outfit. Let's assume that an outfit consists of 1 pair of shoes, 1 skirt, 1 blouse, and 1 jacket. That makes sense, right? She will certainly be wearing shoes. She will certainly be wearing a shirt, right? So an outfit consists of these 4 things. So what you can do is you can think of her dressing herself as a series of 4 stages. The first thing she does is choose a pair of shoes. The next thing she does is choose a skirt. The next thing she does is choose a blouse. And then finally, stage 4, the last thing she does is choose a jacket. Well, how many ways can she do stage 1? How many ways can she choose a pair of shoes? There are 3 ways to do so. Stage 2, choosing a skirt, there are 4 ways. Stage 3, choosing a blouse, there are 6 ways. And stage 4, choosing a jacket, 2 ways. So that's where this multiplication expression comes from here. 3 ways for stage 1, 4 for stage 2, 6 for stage 3, and 2 for stage 4. Gives you a total number of outfits of 144. Here is an extension of the previous example. Once again, this woman is packing for a business trip. This time she packs 3 pairs of shoes, 4 skirts, 3 pairs of slacks, 6 blouses, 3 turtlenecks, and 2 jackets. Okay, as before, we can assume that she coordinates the colors, so everything goes with everything else. We don't need to worry about that, right? Okay, this time we will define an outfit as consisting of a pair of shoes, a choice of lower wear, so she can wear either a skirt or a pair of slacks, and a choice of upper wear. She can either choose a blouse or a turtleneck, or she can wear both. And finally, she can either choose to wear a jacket or not. Notice how much more complicated this is than the previous example. In the previous example, she had no choice. Well, first of all, there are fewer stages here, right? Just skirt, blouse, jacket, and shoes. And she had to wear shoes, had to wear a skirt, had to wear a blouse, had to wear a jacket. Now we're saying that there are going to actually be more stages, and furthermore, in some of the stages, where is it? Yeah. In some of the stages, she can choose either to do something or something else, or both, in this case, right? Either a blouse or a turtleneck, or she can wear both. And then the last stage, she can either choose to participate in or not, right? She can either wear a jacket or not. So in this case, how many different such outfits are possible? How many ways can she make an outfit? This is certainly a more sophisticated variation than of our previous example. Our strategy here will be to think of an outfit as being put together in stages, just like we did before, and to draw a box for each of the stages. We then separately count the number of choices at each stage and enter that number in the corresponding box. The last step is to multiply the numbers in each box, which we're going to do next. So here you go. At stage 1, when she chooses shoes, she has 3 choices. She must wear shoes, and she's packing 3 pairs of them. At stage 2, she must wear pants or a skirt, right? She's not going bottomless here. How many choices does she have at stage 2? Well, she packed 4 skirts and 3 pairs of slacks. So there are 7 total ways she can do stage 2. Okay, choose upper wear. How many ways can she do that? She can either wear a blouse with no turtleneck, and since she packed 6 blouses, there are 6 ways to do that. She can wear a turtleneck with no blouse. Since she packed 3 turtlenecks, there are 3 ways to do that. Or she can combine the two. So this thing here is like a sub-stage, if you like. Here she's choosing a blouse followed by choosing a turtleneck. Well, there are 6 ways to choose a blouse and 3 ways to choose a turtleneck. So the multiplication rule says there are 18 total ways of choosing both a blouse and a turtleneck. So you see, this is one of the nice things about the multiplication rule. We're doing a global thing here with 4 stages, right? But down in here we have like a sub-stage, or whatever language you want to put there. Here's a piece of stage 3 that is itself 2 stages. And so you can use the multiplication rule to get the number there. Again, so if this is not clear here, here are the 6 ways she can wear a blouse without a turtleneck. Here are the 3 ways she can wear a turtleneck but no blouse. Here are the 18 ways she can combine her 6 blouses with her 3 turtlenecks. Finally, at the end here, she can either choose to wear a jacket or not. If she chooses to wear a jacket, there are 2 possible ways to do that because she has 2 jackets. And there's 1 possible way to wear no jacket. So at stage 4, there are 3 possible outcomes. She can wear 1 of her 2 jackets, or she can wear no jacket. So in the end here, we have 3 ways to do stage 1, 7 ways to do stage 2, 27 ways to do stage 3, and 3 ways to do stage 4. When you do 3 times 7 times 27 times 3, you get 1701. Okay, here's another example. 5 candidates are running in an election with the top 3 vote getters elected in order, I'm sorry, with the top 3 vote getters, as president, vice president, and secretary. So the person with the most votes is president, second most votes is vice president, and third most votes is secretary. We want to know how big the sample space is. So we have 5 candidates. We want to know how many ways can you get 3 candidates out of the 5. In order. So how many ways are there to get a president, followed by a vice president, followed by a secretary? So using a box model, we see that this becomes reasonably easy, not trivial, okay, not easy, but manageable to count this sort of thing using the multiplication rule. So at stage 1, again, you're just counting the total number of ways somebody could have this ranking, right? The total number of ways we could have a president followed by a vice president followed by a secretary. So you can think of choosing people in stages. At stage 1, we're going to choose a president. Stage 2, choose a vice president. Stage 3, choose a secretary. At stage 1, any of the 5 people could be president, right? We're not told that any of them are excluded or anything. So there are 5 ways we could complete stage 1. At stage 2, though, we've already chosen somebody as president. That was stage 1. Right, so there are only 4 candidates left when we get to this stage. That's why there's a 4 here and not a 5. If you write a 5 here, it's like you're assuming that the person you chose here could also be vice president. And that's not true. Whatever's name is written here, that name cannot also appear here. So there are 5 ways to do stage 1, 4 ways to do stage 2, and now when you get to stage 3, whatever name is written here and whatever name is written here are now off limits. So there are only 3 candidates remaining here, and therefore 3 options for stage 3. Therefore, the total number of rankings we could see is 5 times 4 times 3, which is 60. So that covers the multiplication rule. Essentially, you can just think of things as boxes, and you just fill in the number of ways each stage can be completed. Before moving on to the other 2 counting methods, we first need some notation, just in case you haven't seen this before. If n is a number, then n factorial, that's how you read this exclamation mark here. N factorial is that number itself times the number 1 less than it, times the number 2 less than it, etc., all the way down to 3 times 2 times 1. So how does this work in practice? 3 factorial, that means start with a 3, then multiply by the number 1 less than 3, which is 2, then the number 1 less than 2, which is 1, and you get 6. 4 factorial, start with 4, then times 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1, etc. Okay? 8 factorial is 8 times 7 times 6 times 4 times 3 times 2 times 1, and so on. Okay, if you don't understand this notation, the following couple of slides will be hard to understand. So make sure you understand what the factorial of a number is. Permutations are an ordered selection of R objects chosen from a set of N objects, where R can be any number between 0 and N. What does that mean? Imagine you are trying to count something like this, much like this actually, where you have an ordered list of things. Okay, here we had president, vice president, secretary, and the order in which we wrote those names mattered. That's very much like what's happening here. You have N things. You want to choose R of those things, and the order in which you choose those R things makes a difference. So permutations are used to count the number of ways you can have a list of size R where the order of things inside that list matters, and you're choosing the items from R from a set of N objects. Okay, so this might sound sort of abstract and confusing right now, but we will do an example in just a second. In the special case where R equals N, what does that mean? N is the number of things you are choosing from. R is the number of things you are actually choosing. So in the special case where R equals N, that just means you're choosing everything. And a permutation is just a rearrangement or shuffling of the objects. Okay, so that should give you an idea of what's happening here. If we have 5 candidates, and I say to you, hey, how many ways can you choose 5 candidates from the 5 candidates, and the order matters? All I'm really telling you to do is just shuffle the 5 people. Right? You're not changing the number of people you are looking at. The number of permutations of a set of size n, where you're choosing R objects from that set, is denoted subscript n p subscript r, and that's used to denote this fraction. N factorial, which is again is n times n minus 1 times n minus 2, etc. divided by the number n minus r factorial. Okay, so I show this to you just to show you what the definition is. Most calculators will compute NPR for you, so you can just compute it on your calculator. I don't care. What matters here is that you keep in mind why you would even be calculating such a thing. So the key thing to take away about what permutations do for you is they count the number of ways you can choose R things from N things, and the order in which you make your choice matters. Here is an example. Suppose there is a hat with 30 numbers in it, and those numbers are 1 up to 30. 6 numbers will be drawn. To play the lottery, you will fill out a ticket with 6 slots. Okay, so your ticket may look something like this: 1, 5, 29, 6, 7, 8. Suppose that these are the rules of winning. To win the lottery, you must choose the 6 numbers drawn and the order in which they were drawn. Okay, so if this is your ticket right here, 1, 5, 29, 6, 7, 8, if the ticket, if what is actually drawn from the hat are these 6 numbers but in a different order, then you don't win, according to this lottery. So imagine that the lotto runner, whatever, the guy who actually draws the numbers out of a hat, draws 6, 7, 8, 1, 5, 9. Those are your 6 numbers, but they don't match the order in which you wrote them down, so you wouldn't win that lottery. So the question is, how many ways can you fill out a lottery ticket for this lottery? If you think about it, what we're really saying here is, how many ways can you choose 6 objects from 30 objects? Okay, so just think of all of these numbers here as just slots of paper, right? You have 30 slots of paper. How many ways can you choose 6 slots of paper? Oh, and by the way, the order in which you make your selection matters. Okay, so how many ways can you choose 6 things from 30 things, and the order in which you write things down matters? That's what this question is asking. And how many ways can you fill out a lottery ticket? This ticket is different from the ticket 5, 29, 6, 7, 8, 1. Okay, that's a different order. Well, the answer is NPR, where N is 30 and R is 6, because that's what this is counting. This thing is literally counting the number of ways you can choose R things from N things, and the order matters. So you would just, again, on your calculator, ask it what 30PR is, or you can ask Google Calculator, whatever. If you have trouble actually getting this, if you don't know how your calculator does it, or you're having trouble getting the Google Calculator to tell you, then just email me. I'll show you how to do it. But don't lose sight of the big picture here. Why is the answer this? Why is the answer 30P6? Because again, you are choosing 6 things from 30 things, and the order matters. Okay, by contrast, suppose you're choosing R things from N things, but the order is irrelevant. The order does not matter. Then how do you count such a thing? So how do you count the number of ways to choose R things from N things and the order is irrelevant? And before I show you the formula here, before we discuss it, think about hands of cards. So like a 5-card hand, right? What the hand is does not matter, does not depend on the order in which you hold your cards. So if you have like the 2, 3, 4, 5, and 6 of hearts, right? You can hold that in your hand as a 2, 3, 4, 5, 6, or you can hold it as like a 6, 4, 5, 3, 2. Okay? When you shuffle a deck of cards, it doesn't matter. It doesn't change what the hand is. So if I asked you, how many 5-card hands are out there? Count the number of 5-card hands for me. You would not use this, okay? Because in a hand of cards, the order does not matter. If you're going to use this, you're acting like the order does matter. Okay, so when order doesn't matter, what you do is you take NPR, which is the number we just found, or that we just discussed, and you divide it by something. You divide it by the number of objects you chose, factorial, and here's the exact formula. And again, your calculator should do this for you. If your calculator won't, you can ask me how to do it, or Google how to do it, or use Google Calculator. whatever. Here's the lottery example again, but this time, notice the difference. We still have a hat with 30 numbers in it. 6 numbers will be drawn. To play the lottery, you will fill out a ticket with 6 slots. Your ticket may look like this, again. Here's the difference though. To win this lottery, you must choose the 6 numbers drawn, but the order in which you write down your numbers doesn't matter. This is how many lotteries actually run, I suppose, the majority of lotteries. So if you write this down on your ticket, this 1, 5, 29, 6, 7, 8, if the numbers from the hat actually come out like 29, 6, 7, 8, 1, 5, you would still win that lottery because the order of the numbers doesn't matter. All that numbers are just the numbers themselves. Yeah, so as I say here, if the 6 numbers drawn are 7, 8, 6, 1, 5, 29, right? It's the same 6 numbers in a different order. You still win. Order doesn't matter. Now if you think about the same exact question, how many ways are there to fill out the lottery ticket? The answer now is NCR rather than NPR, because now the order of your numbers doesn't matter. Okay, so, oops, it will give you a different number. That is the conclusion of 16.2. We covered the multiplication rule, permutations and combinations, 3 different ways to count things. In section 16.3, we will apply these rules to calculate probabilities. So see you in section 16.3.